Okay, we have that the directional derivative of f in the direction of u at AB can be found by the gradient of f at AB dotted with the unit vector u. Now recall back in chapter 12, we could get the cosine of an angle between two vectors. Let's say the two vectors are u and the gradient of f at AB. So it'd be u dot the gradient of f at AB over the product of the magnitudes. So that's how you found the angle between two vectors. So I'm going to take this equation and solve it for this dot product. So I'll have that this is equal to the magnitude of u times the magnitude of the gradient at AB times cosine of the angle between them. Okay, so I want to find if I've got a gradient and a vector u, which is given in the xy plane. The gradient's also a vector in the xy plane. So I want to find out how these two are related, the direction we're trying to move in and the gradient. And we're going to look at that angle between the two. Now recall that u is a unit vector, so the magnitude of u is just 1. So this becomes just the magnitude of the gradient times the cosine of the angle between them. So this is how we can look at that directional derivative. Now, remember that the values of cosine of theta range from -1 to 1. If I'm trying to determine what is the largest possible value this directional derivative can be, it's going to occur when cosine of theta is equal to 1. And the largest directional derivative then would be the magnitude of the gradient. What that means is that the largest rate of change in z will be if we're moving in the direction that makes cosine of theta 1. Well, let's see, if cosine of theta is 1, that means that theta is equal to 0 degrees. So we're moving in a direction that is gradient. Okay, so u is the direction we want to move. If the angle between u and the gradient is 0, then that means that we have the greatest possible directional derivative. Okay, remember the theta is the angle between u and the gradient. So u is the direction of the gradient. So if we're trying to figure out what direction do we move in order to have the largest possible directional derivative, the largest possible change in the z values, the greatest ascent or the greatest descent. The greatest ascent would be moving upward. The greatest descent would be moving downward the fastest. All we need to do is to find out what that gradient is. The gradient, the magnitude of the gradient gives us the greatest possible directional derivative, and that occurs when the direction we move in, the u, is the same as the gradient. The angle between them would be 0. So f has its maximum rate of increase in the direction of the gradient. So that rate of increase will actually be just the magnitude of the gradient at AB. Okay, now if we want to go down the fastest, when will this actually be the smallest possible value? That'll occur when cosine of theta is -1. And when is cosine of theta -1? when theta is equal to pi. So if the gradient were moving in this direction, then the direction we need to move in, the u direction, would be at an angle pi from that gradient. So the maximum rate of decrease of f goes in the direction of negative the gradient. So it is just the negative of this gradient. And that rate of decrease will be negative the magnitude of that gradient. So if this is -1, the directional derivative will be negative of that magnitude. Now, if we want to have a directional derivative of 0, this value will be 0 if the angle theta is pi/2. So what that means is that if this is given us the direction of the gradient, this would correspond to the greatest increase along the surface. This would correspond to the fastest descent down that surface. Then the direction we would need to go would be perpendicular to the gradient. So we want this angle between the gradient, here's the gradient, the angle between u and the gradient needs to be a right angle. So the directional derivative will be 0 in any direction that's orthogonal to the gradient. So go in either direction orthogonal to the gradient, and you will actually be having no change in z, which means you're going to be moving along a horizontal surface here. Okay, so you're going to be staying on that same level, that same z value, if you move in either one of those two directions. So this staying at the same level on that paraboloid corresponds to moving orthogonal to that gradient. Okay, consider this paraboloid. If you're located on the paraboloid at the point 2, -1/2, 35/4, so here's the 2, -1/2 down in the xy plane, in what direction should you move in order to ascend on the surface at the maximum rate? So we want to have the greatest directional derivative upward along that surface. So we want to figure out which direction we need to go from this point to go upward on the paraboloid the fastest. Okay, well, that path of greatest ascent is determined by the gradient. So the gradient of f will be 2x 6y. That tells you the direction of greatest ascent, and it's based on the point. So look at the x and the y values. So the gradient at 2, -1/2 will be 4, -3. So look at the point 4, -3. We're at the point 2, -1/2. So we're right here. And now we're going to go in the direction of 4, -3. Remember, if you were plotting that 4, -3, you would actually plot it as 4, -3. It would be this direction. But we can put that here at this vector and make it a unit vector. So we just want to move parallel to that gradient. So we want to go in that direction. Okay, so in which direction should we move? We should go in the direction of 4, -3. But if we want to give that as a unit vector, the magnitude of this gradient is 5. So the unit vector will be 4/5, -3/5. And if we want to know that maximum rate of change, the maximum rate of change is the magnitude of that gradient, which is 5. So if we move in this direction, you'll be going up the curve the fastest at the rate of 5 z values per unit along that vector u. So that's the path of steepest ascent, and the maximum rate is 5. And what direction should you go in order to descend at the maximum rate? Well, that's just the negative of the gradient. So that'll be -4, 3, or given as a unit vector, we'll go in the direction -4/5, 3/5. So now that would be moving in this direction, which would correspond to going down the curve, down that paraboloid, and at the rate of -5. So it's going to be just the opposite, the negative of the rate that you're going up. You're just changing the direction. Okay, at the point 3, 1, 16, in what direction is there no change? Well, for there to be no change, we know it needs to be perpendicular to that gradient. So if our gradient is 4, -3, perpendicular to it, let's see, this will be over 4, down 3. Now, if I wanted to find okay, they've changed points on me, so let me come back over here. We're now at the point 3, 1, so let's find the gradient of f at 3, 1. The gradient we found here. So at 3, 1, it will be 6, 6. So that's the gradient. Now we're in the xy plane. So to move so that there's no change in the function, the vector u, the direction we want to move in, let's see, now this is the direction. I'm just going to get a vector that's orthogonal to 6, 6. I don't really care where the point is at right now. So what I want to find is something orthogonal to this. Now this vector, you have a couple ways to do this. The simplest thing would be just to think, okay, I'm trying to find a vector here. Let's call it CD, so that this dot product is 0. Okay, to be orthogonal, this is the direction, and it needs to be orthogonal to the gradient. So what vector would be orthogonal and cause there to be a dot product of 0? So you could solve that if you want to algebraically. 6c plus 6d is equal to 0. So that means that c is actually equal to -d. So you could just pick anything. You could pick, let c be, let's let c be 6, or d be 6, and that means the c is going to be -6. So just find a vector. It's real simple just to pick the opposite of one of these two. Just pick the same numbers, reverse them, and get it so the dot product is 0. So another way to do it, doing a graph, it'd be if this is 6 and this is 6, so we have the point 6, 6 up here, then this line that is going to be orthogonal to it would be going down 6 and to the right 6. So down 6 and right 6 would have a slope of -6/6, a slope of -1. So if you just want to get a line that has slope -1, so down a slope of -1, it's going to be a line like this. So if you want a unit vector, it would actually be -1, 1 would be a possibility. Actually, it doesn't really matter. Just make one of them the opposite sign and make the numbers the same in this case. So in what direction is there no change? You could say -1, 1. You could say -6, 6, 6, -6. So any multiple of that. So -1 over the square root of 2, 1 over the square root of 2 would be one way to write it. So if you want a direction, they'll give it as a unit vector. So take whatever you come up with and write it as a unit vector. or the opposite direction would be 1 over the square root of 2, negative 1 over the square root of 2. Okay, considering this function, compute the gradient and the gradient at the point 2, 3. So the gradient for this function would be 6x minus 4y. So the gradient at 2, 3 would be equal to the vector 12, negative 12. So now I want to find a unit vector. I'm going to assume that it's given as a cosine theta, sine theta, because what I want to find is I want to find what is the value for theta. So that's the angle measured from the gradient. So that, well, it's the angle measured from the positive x-axis, but it's the angle between, I want to find what the angle is that would actually give us that direction that was, the directional derivative will have the maximum minimum values. So the gradient is 12, negative 12. And now I'm going to use the vector u, and I want it to be the maximum value. So if I'm going to have the maximum value, let's look at the vector 12, negative 12. We know this is the direction to get the maximum value. So we just want to figure out what that angle is. So 12, negative 12, let's see, 12, negative 12 would be down here. Over 12, down 12. So that's the direction that's the direction of the gradient, and that is the direction where there's going to be the maximum directional derivative. Okay, so now if you want to find that angle made with the positive x-axis, you can do so by just remembering that if you're given a point, you have this terminal point 12, negative 12, tangent of theta is the minus y over the x. So minus 12 over 12 or negative 1, and that's when the reference angle, so the reference angle is going to be pi over 4, but for tangent to be negative, we have to be in quadrants 2 or quadrants 4. So the angle in quadrant 4, which is obviously where this gradient is pointing, 12, negative 12, would actually be 7 pi over 4. So that's the angle all the way around here. Now that's where there's the maximum increase. So the maximum directional derivative is when theta is 7 pi over 4. The minimum directional derivative will be in the opposite direction of the gradient. Well, the opposite direction of the gradient would be going in this direction. And we know that angle is just going to be 3 pi over 4. Okay. Okay, now if we wanted to know, well, it doesn't ask, if you want to know in what direction would there be no directional derivative, no change in the z values, it's going to be orthogonal to that, and that's just going to be going straight through here. So no directional derivative, that means the directional derivative is 0 if theta was pi over 4 or 5 pi over 4. And now if you actually want those directional derivatives, the directional derivative is the magnitude of the gradient. So So that's the magnitude of 12, negative 12, which is 12 times the square root of 2, which is approximately equal to 17. So that's the maximum directional derivative. The minimum directional derivative would be negative that.